Question 4. Show that if limit n tends to infinity of an is equal to L for some L, then the sequence an is bounded. So here I wrote the definition of limit of an as n tends to infinity is equal to L. It means that for any epsilon positive, there is big N. This big N, I can always choose it to be an integer, such that for all n that is bigger than n, absolute value of an minus L is less than epsilon. We want to show that we can find big M such that the absolute value of an is less than or equal to big M for all n. Okay, this is to show that an is bounded. Okay, so what can we do? Maybe you can say that why don't we take M to be the maximum of everything, right? Of everything. Absolute value of A1, absolute value of A2, absolute value of A3, absolute value of A4, and so on. Then I'm sure that all of this, okay, the absolute value of an must be less than or equal to this, because absolute value of a1 is less than this, right? But you cannot do this. You cannot do this because we don't even know whether there is actually maximum value from here, right? There are infinitely many elements to compare. So you cannot do this. Okay? You cannot do this. So what can we do? So proof. Okay, so we know that limit n tends to infinity of an is equal to L means this. So this works for all values of epsilon. I can, let's say, take epsilon equals to 1. This epsilon is from the definition of limit. Okay. Then we can find an integer big N such that for all small n bigger than this big N, we have absolute value of an minus L is less than 1. Right. And we see here we have for all n is bigger than big N, absolute value of an minus L is less than 1. If from here I can transform into absolute value of an is less than or equal to something, then it means that for this case we have found the bound for an, right? So our aim now is to get this. So this means I want to get the form absolute value of an, so we can make use of this trick. This is more than or equal to absolute value of an minus absolute value of L. Okay, and we see from here and here I can write minus 1 is less than absolute value of absolute value of an minus absolute value of L less than 1. I add absolute value of L all sides. I will have minus 1 plus absolute value of L is less than absolute value of AN is less than 1 plus absolute value of L. But this means absolute value of AN is strictly less than 1 plus absolute value of L, right? So strictly less than 1 plus absolute value of L. But what we want is less than or equal to. But can we just add equal sign here? Yes, because if absolute value of AN is strictly less than 1 plus absolute value of L, this means absolute value of AN is less than or equal to 1 plus absolute value of L. So we have shown that for all n is bigger than big N, we can find a real number so that absolute value of AN is less than or equal to that real number. Very good. So let's take a look at this sketch. Okay, so what have we done here? Let's say let's say n is here. This is n. So what have we shown here is if small n is bigger than big N, everything here, okay, everything here is bounded. So what we need to do now is just to deal with this part, because if this part is bounded, then we are sort of done, right? And we see that there are only finitely many terms here. So we have absolute value of AN is less than or equal to the maximum of absolute value of A1, absolute value of A2, and so on until absolute value of A of big N for all n less than or equal to big N, right? This is because absolute value of A1 is less than or equal to absolute value of A1, absolute value of A2 is less than or equal to absolute value of A2 if I want, and so on until absolute value of AN is less than or equal to absolute value of AN. If you want a maximum, okay, if I want all of big N, the value that is bigger than or equal to all of this value, I can just simply take the maximum of this, right? So the absolute value of AN is less than or equal to the maximum of absolute value of A1, absolute value of A2 until absolute value of A of big N. And now what we need to do, we have for all n is bigger than n, we have this. For n is less than or equal to big N, we have this, right? So for all n, we have absolute value of AN is less than or equal to the maximum of absolute value of A1, absolute value of A2, so on until absolute value of A of big N, 1 plus absolute value of L for all n, starting from 1, 2, 3, and so on. It means that we can find a real number such that absolute value of an is less than or equal to that real number. This means the sequence an is bounded. Okay. Yes. Done. Okay.